So some Chem 1 knowledge. It's your polyatomic ions. Given a name, can you write the formula and its charge?
Sulfates SO4 2-.
Very good. What about nitrate?
Is it NO4 2-?
No.
It's NO4.
No. NO3 and the charge. So you want to have these memorized. Now if we hook up a hydrogen as a positive charge, what do we get when we hook up hydrogen with sulfate? Really strong acid. That is the whole point of this discussion. How do you know you're dealing with an acid? Yeah, it has hydrogen in it. Is ammonia typically an acid? In organic chemistry, we make it an acid, but based on your Chem 1 knowledge. Not really. It's a Arrhenius base. You add it to water. There's our equilibrium arrows. You're going to get the ammonium cation and hydroxide. So we typically call this a weak base. In OChem, we can call it an acid and yank the proton off the sign. But here we don't do that. These are all strong acids. What does that mean? How do you know they're strong acids? Well, right now, because I'm telling you, and if you want to learn that all these polyatomic ions, if I hook them up with hydrogen, then they become acids, and they're all strong because they completely disassociate. So I'm going to just pull out nitric acid. Maybe I'll get into that aqueous stuff. So I don't write an equilibrium arrow. I write a normal arrow like that. Strong acids completely disassociate. So I have no HNO3 anymore. I have hydronium ion and nitrate. And of course you might be used to seeing it like this. And that's a fine way to look at it, but from now on, we want to realize that acid-base chemistry requires solvent, and an acid or base can have different strength depending on which solvent it's in, and we're going to just focus on aqueous acid-base equilibrium. So there's our introduction. Might as well do this since we're here. Every acid-base reaction requires an acid and a base. So water's behaving as a base, so this thing called hydronium we'll call a conjugate acid, and nitrate we call it the conjugate base. So acids taste sour. Think of a lemon, citric acid, and acids can cause dyes to change color. We'll see that with acid-base indicators. Bases taste bitter and feel soapy. A real bitter base would be caffeine. That's why coffee tastes so bitter. I don't think coffee has enough base to feel slippery, but in the lab, when you put 1 molar sodium hydroxide on your fingers, it feels slippery. Of course, label falls off a bottle, and I want to figure out whether it's acid. That's what I do, is I pour it on my hand. Probably not OSHA-approved testing method. All right, so I just said ammonia was an Arrhenius acid. Because we saw we put ammonia in water, we increase hydroxide ion concentration. Or we saw hydroxide ion get formed. So a good example of a Arrhenius base. You add this to water, it increases hydroxide ion concentration. So we have another definition, the Brønsted Lowry acid-base definition, and it focuses with the proton ion in water. Proton ion is simply a proton with no electrons. If it had electrons, we'd call it a hydrogen atom, I guess. And in water, the proton isn't gonna just exist by itself. I mean, that's a pretty healthy charge, and water has a dipole. So it says here the simplest cluster that this thing forms clusters with solvent. It's actually more than one water molecule, but here we can imagine one water molecule forming a cluster. Actually, we're going to show water being protonated here in a second. Fortunately or unfortunately, we use proton and hydronium ion interchangeably. So we'll close with this idea. Here's HCl. Here's water. This looks like an acid. Has hydrogen on the left. Oh, water. says hydrogen on the left as well. Turns out water is amphoteric. What does amphoteric mean? Absolutely. It can behave as either an acid or a base. It can behave as a base because it has unshared protons that can accept a proton. So these electrons can grab that proton. Those electrons will jump there. So now we can see we form this conjugate acid, and chloride is a conjugate base. So there's your introduction to acid-base equilibrium. No equilibrium arrow here, because it completely goes to this side. So while you're packing up, I like to ask the students, how do you know if you have a weak acid? And you might say, well, it doesn't completely dissociate. And I'm like, all right, well, out of a list with no numbers. And the way to know if you have a weak acid is to know that it's not a strong acid. So the reason why I put these up here, if you memorize these, they all form strong acids. These aren't polyatomic ions, but these all form strong acids as well. Towards the end of this chapter, we'll look at structure. I used to have 7, I'm missing 1. But if you know these 6 as strong acids, it's not on this list, it's probably a weak. So that's your knowledge nugget to help you.